In this video, we're continuing section 2.2 on the derivatives of vector functions by doing example 2.2.2. Here we're given the vector function in two-dimensional space. R of t is t cubed and t squared. And we're first asked to find the tangent vector, the unit tangent vector, for any t where the expressions are valid. So we have to remember what these are defined as. And the tangent vector, you'll remember from the last video, is just another notation for r prime of t. And since we have a vector comprised entirely of polynomials, taking the derivative is very easy. So we get r prime of t, which is t of t, is 3t squared and 2t. Now we also want t hat of t, which is 1 over the length of r prime of t times r prime of t. So we need the length of the derivative vector. And so let's calculate that down here first. The length of r prime of t, it's the norm, the same way you would calculate the norm of a constant vector, so the square root of the sum of the squares of the components. So t, nope, r prime is not t cubed, that's r, 3t squared plus 2t squared, the square root of that. And so we have here the root of 9t to the fourth plus 4t squared. That's the length of the derivative vector. So the unit tangent for any place that we can divide by this quantity is 1 over the square root of 9t to the fourth plus 4t squared times the derivative vector 3t squared 2t. Now in part B we're asked to graph r of t, r of 1, t of 1, and t hat of 1. So r of t, the graph of this planar curve, well, there's a couple ways of doing it. So first thing that we might notice is the relationship between y and x, and y is x to the 2/3. That is the cuspy looking curve that we have seen before in a previous video. So we need to put that on the axes, and so I'm going to choose a couple of t values. If we go, for example, at t equals 0, then I get the vector 0, 0, and the vector 0, 0 is here. If I look at t equals 1, then our graph is going to pass through the point 1, 1. And when t is equal to 2, we're going to have the point 8, 4. So 8, 4 is here. So our graph will come up and look like this. And if I look by symmetry and the negative values here, the other side of the graph is going to look like this. Now we're asked to draw, so there's the curve, r of t, r of 1. So as I had done here, r of 1 is the radial vector or the position vector. R of 1 is the vector 1, 1. So that's r of 1 done, t of 1. So I'm plugging t, not t hat, t of 1 into the formula that we had for here, right? T of 1, so we're getting 3, 2. And I'm going to draw that starting at that same position. So if I go over here 1, 2, 3, and up 1, 2, then the tangent vector is, doesn't look good there. Let me draw that again. There. So the tangent vector t of 1 is in green. And I also want t hat. I want the unit tangent vector. And so t hat of 1, I'm going to use the t hat formula here. So 1 over, plug in 1, I'm going to get root 13 times the vector 3, 2. which is a unit vector in the direction of the tangent vector. So there is our curve, our radial vector, our tangent vector, and our unit tangent vector all on the same graph. Now part C says, can we identify any places where the graph is not smooth? And we'll remember that for the graph to not be smooth, we need the derivative, the length of the derivative, to be 0, which means that the derivative vector itself must be the 0 vector. There's only one vector with length 0, and that is the 0 vector. The derivative vector is the vector 3t squared and 2t. We need that to be equal to 0, 0. And the only t value that will do that for us is when t is equal to 0. So when t is equal to 0, the graph of r of t is not smooth. And if we look on the graph that is up in part B, we see exactly what that point looks like. The point that is not smooth is exactly the cuspy point of the origin. Let's go and look at a little animation of this curve with tangent vectors moving along in the direction of the curve to see what that looks like, and then we'll come back and do takeaway 5. So here is an animation of tangent vectors moving along our plane curve. R of t is t cubed and t squared. And as you can see, the vectors are changing length as the t values increase as we move along. The advantage of the unit tangent vector, of course, would be that it is always length 1. So a unit tangent vector, you would see the direction of the curve, but the vector would not change in length. All right, so takeaway 5, the unit tangent vector t of t naught gives the instantaneous direction of the curve r of t when t is equal to t naught.